Good morning, everyone. I think I see you if I do that. So, welcome to Zen and the Art of Code Lifecycle Maintenance. I'm Phil Nash, one of the two Phil Nashes here this week, actually. Make it extra confusing, we both work at Sonar. You can meet us both on the booth we have down on the floor. If you want to reach me, I'm Phil_Nash on Twitter. The other one is just Phil Nash on Twitter, so make sure you get the right one. If Twitter's not running, it's often not these days, I'm also on Mastodon, so all my details are up there. Now about this title. Now for those of you that don't read abstracts for talks or books, in fact, this is based on the title of a book, Zen and the Art of Motorcycle Maintenance. And if you have read the book, actually, show of hands, who's read the book? So, yeah, three or four people. Well, if you have read the book, you know that it's not particularly about Zen or motorcycle maintenance, although both of them do feature from time to time. And this book's no different. What the book is about is quality, and trying to define quality. And that's sort of what this talk is about as well, but in our case, it's software quality. You won't be surprised to hear. What do we mean by that? Well, that's going to be a subject we're going to address early on. But before we get to that, a little bit more about myself. I've done lots of talks over the years in different domains, and I actually keep track of them on my website. They actually go back to 2004. But I was counting them up recently, and apparently since 2015, I've done 120 talks. And in fact, that was a couple of years ago I took that, and I think it's closer to 140 now. Far too many talks. So I've covered lots of different subjects. And what I found was many of them actually related to software quality. It's been a keen interest of mine over the years. And I sort of broadly categorize them into these four buckets. Lots of talks about testing, a few talks about functional programming, some talks about error handling, and some talks about simplicity. And some of those I've done at NDC conferences before as well. But even between those four, there was a common thread. And that thread, well, we've already said it, is the software quality in general. So let's come back to that question then. What actually is software quality? In the book, that's the whole subject of the book, what is quality, and how it's pretty much impossible to really define it. Can we do better with software quality? Well, there's a blog post a couple of years ago now on the shape of code, which is a blog sort of dedicated to evidence-based software engineering. So it's quite a good one to follow. And the title was The Aura of Software Quality. And here he takes on that same question. The conclusion in this article, well, actually, before we get to the conclusion, this comment was quite interesting. It says, people in industry are very interested in software quality, and sometimes they have the confusing experience of talking to me about it. So might give you a little hint as to what the author thinks about software quality. He goes on to say, software quality is a meaningless marketing term. And I can understand why he draws that conclusion. I don't entirely agree with it, but there is some substance there. And the problem is about that defining what software quality is. And the problem that the book has is that, you know, we know it when we see it. You say, yeah, that's got quality, but we can't define what it is. It's very difficult. So here is the book. As I say, this book tries to define quality and ends up splitting it into two types of quality, what it calls classical and romantic quality. More about the how things work versus the how things look or how they're used. And we have that in software as well. I actually found that the follow-up book, which is less well known, called Lila, was even more interesting. And there, he splits it into static and dynamic quality, which are terms that we use a lot in software as well. But the specific meaning in that book is that static quality is quality that's always there. It just permeates the whole thing, whereas dynamic quality is more about sort of the leading edge of reality, things as they happen in the moment. So you're here watching me talk now, There will be people watching this on video later. So you're experiencing the dynamic quality, and people later will experience the static quality. And it's the same event. It's quite an interesting way of looking at it. That's not really what we're going to be talking about today. So let's try and find some better examples of definitions of software quality. So you might turn to Wikipedia. And there is a whole page on software quality on Wikipedia. Lots of quotes from different industry experts, mostly systems theorists, it turns out, have things to say about software quality. I picked out a few choice quotes here. I'm not going to go through them all. But there's just one I wanted to draw attention to at the bottom. I really like this one. I think it gets to like the vagueness of it all. Quality is value to some person. It's not a bad definition as it goes. If you go with this, you won't go too far wrong. I didn't find it quite satisfying enough, though. So we all have our own ideas of what constitutes software quality, and that's really the problem. It'd be nice if there was just some standardized definition of what software quality is that we could all measure against. That would be great. Well, it turns out that there is an attempt to do this. There is the Consortium for Information and Software Quality, CISQ. It's a whole website, you can go look it up, and they have a definition of what they think software quality is. So let's have a look at that. Actually, in the book, they divide it into two things first. One of them is more about how things actually apply to the problem. But then it talks about structural quality. And this is usually what we're thinking about when we're talking about software quality in our code. So it says software quality refers to the software's security, reliability, performance efficiency, and maintainability. There's a nice list. We like lists. We can get our heads around those. Let's pull that out. Now, before I actually looked this up, when I was first preparing this material, I had my own list in mind. I'm going to put that up and see how it compares. So these were 4 of the things from my list. Now, correctness and security are certainly not the same thing, but there's enough of an overlap that I'm going to say, well, that does correspond to some degree. Doesn't really get to the aspect of safety so much, but that's a whole other talk. Reliability, okay, we both got that. I like the way they got performance efficiency. I have performance/efficiency. I think that's a pass. And they got maintainability, and I split it into malleability and evolvability. You know, how you can change things for the current design and how you can evolve it to new designs over time. Well, they're all part of maintainability. Maybe maintainability is the better word. So hopefully those things are all non-controversial. I had a couple more, though. So one that I think is also really important is reasonability. And probably they think of that as part of maintainability, but I think it stands on its own. In fact, it runs through all of the others and also stands on its own in its own right. The ability to reason about code, how quickly you can understand and comprehend it, especially blocks of code in isolation. We often hear the term local reasoning, the ability to reason about it without having to consider everything else. So that one for me is a separate point as well. And the other one I had was applicability. I'd say that one corresponds to the other branch of quality that CISQ defines straight away. So they did get that as well. So I was quite happy with how well this corresponded. I think we're onto something here. So I'm going to stick with my list. And now we have a list. Whenever you have a list, it's tempting and sometimes valuable to take the first letters and see if you can make an acronym out of them. So you can have a name that you can refer to them all by. Unfortunately, with these letters, the best I could come up with was, you arrange them this way, you get Mr. Crap, which wasn't particularly compelling. So I had another go, and those ones with the slashes in, I thought we take the second words, evolvability and efficiency, and then mix those up a bit. Then we can get career. At least that's an English word that we can get our heads around. I don't really think of myself as a career programmer, but yeah, it works. It works. So here you go, the career principles. That's what we're going to talk about. Whatever you call them, these are the 6 software quality principles that I've spent a lot of my speaking career talking about. And I've done many talks on various of these bubbles. Today I'm going to do something slightly different. I'm going to talk about some of the intersections, where these overlap, where there are tensions, trade-offs, or where they work together to give you something even more, or whether they even have a life of their own. I found that really useful, and not something that we often discuss so much. So we're going to take a look at a few of these, and I'm going to start with the intersection of applicability and correctness. Now, we sometimes talk about this in terms of doing the right thing versus doing the thing right. And these aren't in tension, except we have to decide on the order we're going to approach these. Do we do the right thing and then do the thing right, or the other way around? And we usually say this is the correct way to do it. Do the right thing first, and then do it right. Then do it more correctly. And you've probably heard this quote. Well, we usually quote from Russell Ackoff, one of those systems theorists we talked about earlier. He says, it's better to do the right thing wrong than the wrong thing right. And the full quote, you may be familiar with, the righter we do the wrong thing, the wronger we become. When we make a mistake doing the wrong thing and correct it, we become wronger. When we make a mistake doing the right thing and correct it, we become righter. Therefore, it's better to do the right thing wrong than the wrong thing right. Which makes sense. It sounds good. We've been quoting this for years and almost not questioning it. But actually, he goes on, and you're not going to hear this quote very often, for good reason. This is very significant because almost every problem confronting our society is a result of the fact that our public policymakers are doing the wrong things and are trying to make them righter. Doesn't sound like software quality at all. He was talking about society, politics, that sort of thing. He's a systems theorist, not a software quality theorist. And sometimes these things transfer between systems domains, and sometimes they don't. We can't automatically apply them. Does this actually apply to software quality at all? We've been saying that it does for decades. One person to challenge that is Alan Kelly, someone I know from the Agile community. He did a talk a few years ago now, flipping that on its head. He says, do it right and then do the right thing. And the centerpiece of his talk is this slide. This really captures the essence of it. He calls it the alignment trap. And this is based on real data. There's a study that's cited down the side he draws all the data from. But he takes out two key metrics from this data, spread across many organizations, their IT spending and their sales growth projected over 3 years. And then he plots it in this quadrant diagram. Obviously simplified a bit. And so you have the axes, the doing things right axis, from less effective to more effective, and then up the side, doing the right things is less aligned with the business interest and more aligned. Now clearly we want to be in that top right yellow quadrant, the IT-enabled growth. But predictably, only 7% of companies are, so the minority in the data. But they have low IT spending, actually negative, -6%, so it's going down over time. But very high sales growth, 35% there. So yeah, no surprises, that's the best one to be in. Great. Also no surprise, most companies end up in the maintenance zone, the bottom left. So 74% average IT spending, low sales growth is actually going down. So yeah, not ideal. But most companies end up there. What is more surprising are the other two. In particular, the one that's called the alignment trap. So this is more aligned, but less effective, i.e. following Ackoff's advice. And he says, well, they've got actually quite high IT spending. In fact, the highest of all of these quadrants on average. And very low sales growth, the lowest. This is actually the worst quadrant to be in. Surprisingly, even worse than the maintenance zone in many ways. And the other thing that Alan talks about is how hard it is to move from that left-hand side of the graph to the right-hand side. Because you're doing things the wrong way, you don't have that agile mindset that enables you to move easily. So you're trapped there. It's the alignment trap. Whereas well old IT, the bottom right, keep having to reverse it, very low spending, decent sales growth, only a third of the IT-enabled growth, but still the second best on the board. It's actually a pretty good place to be. Doing the wrong things, but doing them very well, and easier to move up. This is where we want to start. Now, I haven't gone back and checked Alan's figures. I haven't checked that study to make sure this actually bears it out. And he actually said in his talk that he was surprised by these findings. He wasn't quite sure if this really held, whether it was just an anomaly of the data or something. So he presented it as, well, these are my findings. Anybody got any data to prove me wrong, let me know. And that was some years ago now. So I asked him just recently, what do you think about it now? And he said in the years in between, everything that he's seen has strengthened his conviction that this is the case. That it's better to do the right thing wrong. Sorry, the wrong thing right than the right thing wrong. The opposite of what we usually taught. There's a lot more to the talk, so I encourage you to go and watch it. Oh, by the way, at the end, I'll give you a single URL with all the references to all of these other talks and links and things. So don't worry about making notes now. Do encourage you to watch the rest of the talk, very interesting. That's what I wanted to talk about for the moment, with the intersection between correctness and applicability. Quite surprising. So let's change gears a little bit. Look at another two. We're going to look a bit closer to the code now, with correctness and reliability. Now, the union of these two really is mostly the domain of what we might call code coverage. And if you've used a code coverage tool before, you know that this is the amount of your code that's covered by tests, usually. But it really breaks down into line or statement coverage, which is nice. It gives you something to measure, but it doesn't actually tell you how much of the code is really covered. We really need to consider branch coverage, or I like to call it data coverage, because from the outside, that's what we're really concerned about. What values can we pass into these things? And there's not really any tool that's going to tell us that. It's a pretty intractable problem beyond anything non-trivial, or anything trivial, shall I say. So we have to sort of leave that to a bit of guesswork, at least in terms of measuring. But there are things we can do to improve our branch coverage, the different types of testing. So one thing that you should look at, if you haven't already, is property-based testing. Property-based testing, if you don't know, looks very much like unit testing, but rather than testing specific examples of things, you're testing for properties that always hold, and then you can throw large amounts of data at it, often randomly generated, and just see if these properties always hold. And over time, you will gradually cover more and more of the domain of values. So it's a really useful way to augment your unit testing, catching all the things you didn't actually think of. So if you haven't tried property-based testing already, I'd encourage you to do so. There are frameworks dedicated to it. There's extra features that they have. But even in your unit test frameworks, there are usually facilities for generating data that you can use the same way. But you need to think about how you define properties first. I'm not going to go into that in a lot of detail today. Similarly, but a little bit high level, fuzz testing. This is more of the system test or acceptance test level. But a similar principle, you're pushing data in, seeing how things behave, whether properties hold, whether it crashes, whether it's vulnerable. It's often used for testing for vulnerabilities. So again, if you're working at that level, I encourage you to check out fuzz testing. And don't forget manual testing. As developers, we're so much focused on how things are implemented, how they should be designed, that we don't have that mindset for breaking things so much that manual testers are really skilled at. So yeah, we haven't automated the manual testers away yet. Maybe ChatGPT will get there at some point, but for now, there's still a role for manual testing. Don't rule that out. So these should all help us to find those things that we haven't found using our more targeted unit testing. Do make use of them. So that's code coverage, but there's a particular part of our code bases that I think doesn't get enough attention most of the time. And they're often the hidden paths through the code. And there are the error paths. And particularly where we have exceptions. And we're going to start talking about language features in a minute, and I'm going to mostly talk about C# today. Originally I did this in the context of C++. We'll have a bit of that as well later. But most of the ideas generalize pretty well. But there are some differences. So there's two types of error paths. There are what I like to call I/O errors, and some people call them disappointments. These are the predictable errors. Well, they're not what you wanted to happen, but we know they can happen. We'll be disappointed if they do. You know, I tried to open this file, but I couldn't. I was disappointed. I'm going to do something else instead. That sort of thing. So it's more like a control flow style of error handling. I want to do this, but if not, I can do that instead. And then the other type of errors, we'll often call them logic errors, or sometimes just bugs. We expect the system to be in this state. Everything's fine if it is. But if not, then I don't know what's happened. But this is a logic error. All bets are off. And in some languages, that gets more serious than others. As I say, I originally did this in the context of C++, where if you get into that state, you start to query what's happened before, like this time travel effect. It gets very weird. But in any language, it's a bad situation to be in. Now put /contracts here, contracts in the general term, because this is how we tend to define things. We have an interface, so we say, well, these are the valid values that I have functionality for. Outside of these values, I'm not giving any guarantees. That's a contract. And there may be language features to support that. There may not, depending on the language. Let's dig into these two a little bit more. So I think this is a really interesting area. So first of all, let's start with a simple example. Let's say these are C# examples. I should also say I translated this from my original C++ examples for this version of the talk. And I haven't done day-to-day C# for a number of years, so I'm not going to guarantee these are the best ways to do things. But here's a simple example to convert a string to an integer. I'm going to use int.tryParse here. It's obviously not quite how you do it. There's some bits missing. Don't worry about that for now. The point is, this should work as long as the string you pass in actually has an integer in it. If we passed in a string that didn't, what would we expect to get? Now, my reading of things is that I think it's guaranteed to be 0. I should get a default value there, but there were conflicting places that said it's undefined or implementation defined or it's always defined. I don't know. The point is we shouldn't be in that situation. This is not how we want to do our error handling. Even if it's defined, it's not very helpful. We can't distinguish it from an actual 0. So of course we don't do it this way. Silly example, but bear with me. We'll do something like this, because tryParse returns a Boolean. We can test that. And maybe we want to throw an exception instead. Then now we've converted it to a different type of disappointment. It's still a disappointment, but now we're using exceptions for it instead. And now we can distinguish the error path from the happy path. Great. So if it fails, now we get an exception. Tells us a bit more. I'm not telling you anything new here. I probably wouldn't use exceptions for something like converting a string to an integer, though. Obviously, we could just use int.tryParse directly. I don't particularly like out parameters, so I'm still inclined to wrap it. So I might use a nullable type. In other languages, maybe an optional. So now we can return null instead. And if that fails, this is what it prints, nothing. So we'll probably put that in an if statement. And now, if we have a value, we can print it. Otherwise, if we do something else, control flow. That's what we want to do with disappointments. And again, if we now print that, we get something a bit more helpful. So there are a number of ways that we can do these things. Some C# methods here, exceptions, out parameters, nullable types. We don't have a first-party result type yet, as far as I know, as far as I've been able to find. It's been talked about. But you can get third-party ones or write your own. So this is a type that will contain either the value you wanted or a value that tells you what the error was instead. So it's like a mix of the other ones. Or more generally, I know there's been a lot of talk over the years about discriminated unions. Maybe they'll make it into C# at some point. Other languages already have them. More general way of doing result types. There's a lot that we could talk about here, and I have done in the talk mentioned here, that optional is not a failure. I've done that talk in the context of C++ and also Swift. But the C++ one in particular, there's a whole section in there where I weigh up all the different types of error handling techniques, all the costs and trade-offs, and give them a scorecard and see how they all stack up. And then at the end, present a possible optimal way of doing it, which we already have in some languages, like Swift, for example, not in C++, not in C#. So if you're interested, watch that talk. So that's all I'm going to talk about for the disappointments for the moment. I want to dig into a little bit more on the other branch, the logic errors. So let's use a different example. This time converting an integer to a string. But hopefully you can get an idea from the name, month of string, that there's probably a specific range of values of this integer that this function or method is valid for. Is it 0 to 11, 1 to 12? Well, that depends. You've got to document that somewhere. But we'll start with this. The function can actually take the whole range of an integer, which for a 32-bit integer, it's going to be like minus 2 billion to positive 2 billion approximately. But the domain, which is the valid range of values that this function has defined behavior for, has a much narrower range, probably 1 to 12. Okay, we're familiar with this, but this is really, more often than not, when we talk about contracts, we're talking about this difference between a value's range and its domain. So how might we handle that? Well, we could reach for the disappointments approach, in this case throwing an exception. So we'll check that something's in range, and if not, throw an exception. And idiomatically, I think in C# at least, that's probably most often what we would do. But there is a cost involved here. If we know that we're always going to be passing in a valid value, well, we're paying this cost of checking every time. And I've seen code bases where the same value is checked over and over and over again because there's just no trust between different layers of the software. And there's some advantages to that, but it gets very tedious and costly. And sometimes that matters. Often it doesn't, but sometimes it does. So the contracts approach, and I'm going to use the contract syntax that I know is considered deprecated these days in C#, so I'm not suggesting you use this. But it's the most direct translation for my C++ code. You can generalize it to other languages. You can use your own approach. But here we're just going to say, well, we have a precondition that this is true. And you can run it in a mode that checks that at runtime. Ideally, we'll abort the process if it fails. So it's often spelt assert in other languages. But you can also do an optimized build, which doesn't do the checking, but you've still effectively documented that these are what your requirements are. And then it's up to you to remove the bugs, because these are bugs, before you make the call. Now, if you have a function like this, and then you have data that's come from user input or across the network or some untrusted source, then you're going to need to check before you call the function now. There's more of a responsibility on the caller. And there's a little bit of a problem. The requirements are encoded in the function body, and you've got to duplicate them outside. Fortunately, we have a way to avoid code duplication. Extract method. Excellent. We can take that, just the condition, write a separate method for it, and use that both in our contract or disappointment, if you like. But we can also use it, the same thing, before we make the call, and we know that we're checking the same condition. So that's an improvement. That's nice. And it seems obvious, but we often forget this sort of thing for some reason when we're dealing with code like this. It's still not very convenient, though. If you're having to do this a lot, well, it's easy to get wrong or miss or forget. And even if you do it, it's adding extra indentation and code. It's not great. Can we have our cake and eat it? Well, we can obviously wrap that in another function. I'll call this one month as string checked. So this is doing the conditional branch beforehand and then just calling on to the unchecked version. Otherwise, we're in this case treating it as a nullable, or you can throw an exception, whatever your choice is. Okay, that's good. Now we can choose which of these to call. The problem here is the default choice, the one that doesn't have the extra word on the end, is the unsafe one. So I would generally prefer to do it the other way around. So we'll have the unchecked version, well, doesn't check, as the name says, and then the one without the suffix actually does the checking. Safe by default, performant by choice, opt-in. I think we're getting there. This is not too bad, but it's extra work. You've got to remember how to do this. You've got conventions to respect. This all comes up because of this difference between a values or a types range and its domain for a particular function. And some other languages have solved this already to some degree, like Ada, a particularly exemplary example here. If you go to the Wikipedia page for Ada, there's an example on there of a date class, or date record. But note how these types are defined. There's a month type. It's actually defined by range. You can only create months with values between 1 and 12. It's correct by construction. Once you've got one of those months, you don't have to check it. You know what its range is. It matches the domain. That would be nice. Most of us are not working with Ada or languages that have anything like this sort of support, but we can roll our own, and it's sometimes worth it. So we could write a month class. I'd probably write it as a struct in C#, value type, but the principle's the same. So we're just going to wrap the integer property here. Really important to make that private setter. We'll have you do it in your language. We don't want to be able to mutate it after the fact because we want to control it entirely through the constructor so that we can validate it in the constructor. Once it's constructed, it's correct by construction. We know we can always trust it. So we push that validation to the constructor. In this case, we're throwing an exception. But you might actually have a case where you do still know the month is a valid month, and we want to construct one of these. Oh, I should have put that up first. So, again, in the C# case, and I don't know if this is the best way to do it these days, but this is what I would do. I'll add a static function that constructs a month using the object initialization syntax. So we can do that now that we are within the class. And we'll just do our requires or whatever the check is before that. So again, we've got both approaches. By default, normal constructor, it's safe. We get the runtime check. We can opt in to the contract check by using create unchecked this way. And variations like that, you've got to pick a convention and stick with it. But this approach has served me well over the years. It gives us the best of both worlds, safe by default, performant by opt-in. So I don't know if you noticed, somewhere along the way we've got an extra bubble up there, the efficiency bubble, because of that reason. So we're actually looking at the intersection between 3 of these properties now. Okay. That's that set of intersections. The next one I want to look into is between reasonability, how easy it is to reason about your code, and evolvability or maintainability, how easy it is to change your code. And there's an obvious correspondence here, but let's explore that a little bit more. I've done a few talks in several of these areas, so I'm going to do it that way. This is a domain particularly of simplicity. I've done a talk on that, seeking simplicity. Often functional programming techniques, doesn't have to be a functional programming language, but some of the techniques, particularly things like immutability, correct by construction we already looked at, and some others, often implied by the use of simplicity. And, oh, jumped ahead. Actually, let's carry on. Talking of simplicity. Anyone seen the talk by Rich Hickey, Simple Made Easy? A couple of people. So my Seeking Simplicity is partially a riff off of that talk, and I stole these illustrations from Rich Hickey's talk. So if they're familiar, that's why. He defines simple and complex in terms of their Latin roots, simplex and complex, which literally mean either one fold or braid or many folds and braids. So really it's about the crossing over of things, the braiding, interconnecting. And in the simple case, well, you can see, well, it's trivial to follow one of these strands from the top to bottom. You don't even have to think about it. It's just obvious by looking at it. In the complex case, you really have to look very carefully to follow something from the top to bottom. And there's only a few things going on there. And if you think of this as the definition of complexity, and then think of all the things in our code which can lead to these sort of things crossing over, interconnecting, then it's not an exhaustive list, but I think these are typical candidates for things that cause complexity in code. Threading and concurrency is the obvious one, perhaps. But globals and singletons, well, they make every part of your code interact with every other part of the code in ways you might not expect. Any sort of shared state can do that, even just reference types. Mutability, because now to reason about the value of something, you have to consider every line of code that it goes through. If it's immutable, you don't. You always know its value. And so on. I think leaky abstractions is an interesting one. Because abstractions, ironically, are one of our biggest weapons in the fight against complexity, helped us to manage it. But they're also one of the biggest causes of complexity, because they leak. And then you have to deal with the abstraction itself and the thing that it abstracts, mixed together. So it's like a meta-complexity, if you like. And talking of meta-complexities, all of these things can interact. One of the worst one is often shared mutable state with threading. I think 90% of our complexity is right there. And dependencies, we need to manage our dependencies, whether they're between bits of code or between whole modules or libraries, package managers. They're all sources of complexity. I'm sure you can think of more. It's worth identifying them, knowing what we're dealing with, and of course trying to minimize them. There's always going to be essential complexity, but make it only that. And that could be hard. The point of Rich Hickey's talk was that easy and simple are not the same things, and it's often easier to go for the more complex thing. Bring in that big dependency, even though you're only using a tiny part of it, or just reach for that thing over there via a singleton. It might be easier at the time, but it's harder in the long run because of the complexity. So, to lower your complexity, or if you lower your complexity, these are the benefits you can get. Turns out it's much easier to test. All of those things, all of those sources of complexity, make your code harder to test. So if you reduce them, it's going to be easier. Easier to reason about. Well, that was what we started with. But also easier to change. That's the evolvability part of it. Think of nicely factored code. It's always easier to change things because there's less interactions between things, less crossing over. And so my formula for success here is CDD and functional programming techniques. And to really dive into that more deeply, see my other talks, but just to talk a little bit about TDD. By following TDD practices, you're going to get all the problems associated with complexity right at the start, at the point you can actually do something about it. So we often call them design smells, or listening to the tests. If we listen to the tests, we'll know when we're introducing complexity that shouldn't be there, and we'll have a chance to deal with it. Because if not, then the testing becomes impossible, and you can't carry on. So that's my formula for success. Your mileage may vary. We're going to have to move on. The next crossover I want to talk about is between reasonability again and efficiency. Let's bring efficiency back in. And these ones are often in tension, or at least there's a perception that they're in tension. And I want to challenge that a little bit. But often they genuinely are. So We're often told, well, we should write our code to be readable and then optimize it later if we've measured that the performance isn't where we need it to be. But we should make it readable first. And so reasonability is not just about readability, but if we think of it as the same thing, makes sense. Now this tension exists because of this problem. We have the low-level machine, the CPUs, the instruction set, assembly language, but also now much more going on below that. We have heterogeneous computing, all sorts of things we can worry about at the bottom end. But actually where we want to mostly be working is at the high level. High-level languages, high-level abstractions, abstract that machine away. We want to work in the problem domain, not rather than the solution domain. And that's great. We can get a long way there, but if we are writing the most performant code, we sometimes get the tension between those two things. Now in the middle, we have systems languages, C, C++, nowadays we've got Rust, Go, others. Maybe just above that, we have languages like C# and Java that are higher level, but still performance focused. But even within those languages, there's different levels you can work at, different levels of abstraction. All the way down to usually C at the bottom layer. C was originally written to be portable assembler. Only trouble was, or is, that it was the assembler of the PDP-11. You ever seen a PDP-11? Here's a picture of one I think I pulled from Wikipedia. These are not modern machines, not modern architectures. Things have moved on. So even if you're working in C and you're working at the low level, for performance reasons, you may actually be pessimizing your code. Or, at best, not having any real advantage, you're just obfuscating things. Now, it turns out that when you write code that's easy to reason about for humans, it actually makes it easier to reason about to compilers as well. And often the compilers can spot the optimization opportunities that you might not have thought of or have the time to work on. And so by starting with the more reasonable or readable code, that may be the only step you need. So the process is still the same. You start with the readability, you measure, and then you see if you can optimize. But you may find that optimization step will make things worse. Let's look at a concrete example, though. And for this one, I'm going to stick to my C++ code because of the performance focus. But don't worry, we're not going to get too deep. The only thing that gives it away is C++ is the double colons. So pretty simple, straightforward code. We've got an enum. We want to initialize it to a value. But to do so, we need to call a function. And so we can put it in an if statement. The problem here is the word statement. Statement is not an expression. So the only way to get the value out of that statement is via a side effect. So we're going to need to create an uninitialized variable. And in C++, that really means uninitialized. It's just random memory, undefined behavior. And then we're going to assign it a value at runtime based on the branch of the if statement. Doesn't seem like the code is that problematic, but there's lots of issues hiding there. You've got that side effect. You've got the mutability. We can't actually make our value const or immutable because we need to be able to assign to it. And that means that for the rest of its lifetime, we need to be thinking about, has its value changed? Can it change for any reason? Lots of problems. I'm not going to go into all of them now. In this particular case, certainly C++ and many languages will have a similar construct. We have the ternary operator. We can actually convert it into an expression. And that solves all of the issues and more. We can now make it const in this case, or immutable. No side effects, no uninitialized values. And as an extra bonus, we can use type inference as well, because we know that all in one go. So this is win-win. Except that it doesn't scale that well, both in terms of the amount of code. It can easily get very difficult to read. But if you've got more values, if we try this example, now we've got just 3 states. Well, we can't really use the ternary operator for that, not without heavy nesting anyway. We want to go that route. So here we're reaching for a switch statement, again, back to the same problem as before. Now, if you've got a language, which I believe C# has now, like pattern matching, you may be able to use that as a more expression-oriented version. But if not, there's ways to fake it. So whatever language you're using, you can probably do immediately invoked lambda expressions or immediately invoked function expressions. This is the syntax for a lambda in C++. The square brackets is the initializer. I'm not going to bore you with the details of that. The bit to note is the round brackets at the end. It's immediately invoked. So we're only creating the lambda and then invoking it all within the same statement. But that means that although we have statements there, the whole thing evaluates like an expression. We get our value out. We can initialize our variable in place. And we go back to all the same initial benefits. And in this case, although it looks like there's more code, ironically in C++, because of the break statements, this is less code than what we had before. But that may not be the case in your case. But it probably optimizes down to the same as the first example. OK, but that's not better than the first example. Not in this case, because it's just an enum, an integer, really, under the hood. Not really much more you can do than that. So here's an example with a more expensive object. Again, it's C++, don't worry about the details. Just know that it's got two constructors, a default constructor and a more complex assignment constructor. They're both doing work. So when you have that default initialized variable, that's still going to be doing some work that can't be optimized away. So to put it to the test in a similar example, like this with the lambda expression, well, if we did it with the switch, the bare switch statement and an default initialized variable, there is measurably more work going on than this version. And I've tested that, put it in a tool that shows you the generated assembler, and there's a lot more code generated. So this is one case where the arguably simpler example with the lambda expression, when you're used to it, that is actually simpler, is also the more performant, because the compiler can reason about all the guarantees and constraints as well. So that's the main takeaway I wanted from here. There are still going to be cases where the compiler can't do that. You will have to measure. And there may still be cases you have to write something that's less readable. Even then, there's things we can do. So go back to testing, and specifically property-based testing again. Mentioned this earlier. Strictly speaking, what I'm going to show you is not property-based testing, but you can use a property-based testing framework to do this very nicely, or property-based testing facilities in your unit test framework. The idea is, well, let's say you have some algorithm that you've written, and you've written it a nice, readable, clean way. You can look at the code and think, yeah, that looks right. You write some tests, of course. It all seems to work. But you're pretty confident in it. The only trouble is the performance sucks. And that's the thing with algorithms. Algorithms, very often, you need to write much more complex code to get the better performance. So you write your more complex version. Well, here's a trivial interface for two such algorithms, the slow version and then the fast, more complex version. Keep the old one around, because you can then test one against the other. So this is some example code from Catch, my C++ test framework. Other frameworks will have something similar. We're just generating loads of values, and then we are passing them to both algorithms and comparing the result. Simple as that. The more values you test, the more confidence you have that they are working as expected. If you're doing it randomly, over time you're going to get more and more of that coverage. And it works. In specific cases, at least. This can get you that little bit further of being able to reason about the code, but still get the performance. So that's reasonability and efficiency. They are the intersections I wanted to talk about today, or at least that we had time to. We actually got to a few in the end. To turns out you can even sort of link these up a bit if we just boil out the commonalities. And it turns out we've actually covered intersections between every single one of those. So that was nice. It also allows me to organize them nicely across the screen for the next bit, which is where I talk about all the things that we've used to help. So we use the type system, particularly with the contract-based checking, correct by construction, but there's lots of ways we can use the type system to make things easier to reason about. We looked at error handling paths, make sure that we take error handling seriously, we know how it divides up and how to deal with it. And we did a lot of testing. Testing helps in lots of different ways. I've just scratched the surface, really. One thing we didn't really talk about, but turns out helps with every single point up the stack except for the applicability, is code analysis, static and dynamic. Of course, I have to put this in. I work at Sonar. We do static analysis tools. But the cause and effect is the way around. I work at Sonar because this is important to me. So do check that out. I'm not going to say much more about it for now, but we need all the help we can get. So use the tools. Almost ready to wrap up. I wanted to say a little bit more, tie this all together. There was a blog post a few years ago now from Michael Feathers. Probably heard of Michael Feathers. Does a lot of consulting in TDD, testing, all the things around that. But he wrote this post called The Flawed Theory Behind Unit Testing. A little bit of a clickbaity title. It's not really questioning unit testing itself, but it's more talking about mocking as it happens. That's not what I want to talk about here. He goes through lots of different approaches to achieving software quality. And in his conclusion, he makes a really interesting point. He says, in the software industry, we've been chasing quality for years. The interesting thing is, there's a number of things that work. Design by contract works. Test-driven development works. So do clean room, code inspections, and the use of higher-level languages. Interestingly, these are all, apart from maybe clean room, things we just discussed today. He carries on. All of these techniques have been shown to increase quality. And if we look closely, we can see why. All of them force us to reflect on our code. And his conclusion was that really this is the main benefit that we get from our approaches to testing. It's not necessarily the testing itself, it's the focus on the code. And I think he's got a point, even if I don't entirely agree with him, that, yeah, all of these things work. And the more we can use aspects of all of them, the higher our code quality is going to be. So there's our 6 software quality principles. One thing we didn't talk about was Zen, which interestingly is the Chinese word, at least originally, for meditation. We don't think about meditation so much when we talk about software. But if we look at the Wikipedia definition of meditation, it says it's a practice of focusing the mind on a particular object, thought, or activity, train the attention awareness, and achieve a mentally clear and stable state, just to paraphrase. Focusing on a particular object. And Michael Feathers said about focusing on the code. So maybe Zen and quality do actually go together, after all. This has been Zen and the Art of Code Lifecycle Maintenance. There's that link with all of the references that I mentioned on my website, places you can reach me. Thank you very much. I think we have time for questions, if there are any. Or if not, we can go grab a coffee. Oh, we've got a question.
Thoughts about code review and how to make that work as good as we can?
Actually, having trouble hearing over the background noise. Maybe we can...
Code review.
Code review?
Code review.
Yes.
Any comments?
Yes, I didn't really talk about code review except what Michael Feathers said, but it's another thing which focuses you on the code. Well, there's lots of benefits, but that in particular. And you could argue that static analysis is a form of automated code review, but I think it's worth having the human step in the loop as well. Yes, it's another way to increase your quality, if you can afford the time it takes. Yeah. Any others? Okay, well, thanks for coming. Enjoy your coffee.